Okay, page 5, we're going to start talking about how this actually applies to electrons. So we've been talking about light and waves. We're going to talk about electrons. We're going to kind of put everything together. Okay, so I've got 6.3 is the atomic line spectra and the Bohr equation. So Bohr is really, really important dude in developing what we know about electrons and how they behave. And so we're going to talk about some of the things that he discovered today and how they apply in chemistry. So first thing is we are going to talk about excitation of gaseous elements. Now, what is excitation of gaseous elements? That means I'm essentially putting electricity through elements and they light up. Very much like neon lights. Actually, not very much. That's exactly what's happening in neon lights. Okay, so if you electrocute certain elements, you're going to get light given off. Neon specifically gives off a very bright reddish color. Krypton gives off like a purplish color. They all have kind of their own type of light that they give off. Now, not everything gives off light that you can see, but a lot of them do. So this is called excitation. And how we do this is just put them under very high voltage or a high temperature or something. We're just putting a bunch of energy in. So this is elements under high voltage, elements under high voltage, or with a lot of energy being shot at them, produce what's called a line spectrum. A line spectrum. Okay, now I was just talking about neon lights and they only give off like one really bright color, right? But that's because we can actually distinguish between all of the colors that are being given off unless you use something like a prism. Okay, so if you use a prism, what a prism does is it breaks up the light so you can see all the different colors that are within that light. And so if we look at these lights through a prism or it's some type of diffraction glass that breaks it up, we can see all these different wavelengths associated with each element. And actually, these waves that are given off, or these spectrum that we see, are very specific. And why that's important is that each element has its own spectrum, its own lights that it gives off. And we can actually treat these kind of like a fingerprint. Okay, so yours may not be in color, but if you look at this, essentially this is one element and it gets like these multiple colors, a blue and a red light. This one's got some blue and a green. This one has 1, 2, 3, 4, 5, 6, 7, 8 different lines that it gives off. And we can actually identify elements by the light that they're given off. So this is actually how we figure out the elements that are in like stars and things, because obviously we can't go there to see what's there, but the light that's given off, if we run it through diffraction, we can actually break it down, see the wavelengths that are given off and be like, oh, well, that's got to have hydrogen in it. Oh, that's got to have helium in it because it has those specific wavelengths. Excuse me. So this principle is actually very useful for astronomers to figure out how old stars are and what elements are in the stars and things like that. Okay, so like I said, we kind of treat those as fingerprints. So each element has its own. Now, we don't do this very often on Earth, finding the whole diffraction thing, like running it through a diffraction glass, but something that's really useful, and you would use this in lab. I don't remember if we use it in 161, we definitely use it in 162, is called the flame test. So you don't even have to have the diffraction. Certain elements give off certain colors. So if you put, for example, lithium into a Bunsen burner, it's going to give off a really bright red light. Sodium is going to give off yellow. Potassium is kind of purplish. Calcium is this other different kind of darker red color, and barium is green. So we can actually use this to determine if certain elements are present in a sample by the color or the wavelength that it gives off. So we can identify metals this way. So up here, we were putting them under high voltage. Down here, we're putting them in high temperature. Okay, so it just has to have a lot of energy put in and they become what's called excited. Okay, so we can burn instead of putting under high voltage. To excite, what we're doing is called exciting the electrons, and I abbreviate my electrons like that. And then we can identify some elements. Identify some elements. Okay, so that light or that color that we're seeing is excited electrons being energized, and then like they will come back down to their ground state and give off this specific color. So that's what we see a lot. There's actually an equation for this just for hydrogen. So I want to talk about this just for a moment. This kind of led us to Bohr's theory. The specific lines that we see in a hydrogen spectrum, hydrogen only has one electron, mind you, can actually be calculated. Like if we're going to see this red light or this green light or a purple light. Okay, so it's only got a specific number of wavelengths that we're going to see. So like when hydrogen has an electron that gets excited and say it goes into the third energy level, when it falls back down to the second energy level, it gives off red light. When you have an electron that goes into the fourth energy level and it falls back down to the second energy level, it gives off green light. Or you have an electron and it goes to the fifth energy level and falls back down to the second energy level, we give off a purple light. So hydrogen actually has a way to calculate this. So Bohr kind of came up with this. This is the equation. It's 1 over a wavelength equals, there's a constant, 1.097 times 10 to the 7th times 1 over the NF squared. Okay, N is the energy level, and I'll write that over here in just a second. F is for final, minus 1 over NI squared, or the initial energy level. Okay, so I'm going to write over here, N is the energy level that it's in. So it's like where the electron goes and where it goes down to where it usually is, that type of thing. Okay, so it's jumping between energy levels. And that's what happens when we put energy into electrons. They kind of jump between different energy levels. Okay, now the thing is, this equation only works for hydrogen. It would be really great if it worked for everything else, but once you start having 2 and 3 and 4 electrons in there, there's a lot of interference, so we get different wavelengths. So that's why we kind of get fingerprints, but hydrogens you can actually calculate. Okay, so this whole like equation, this relationship between where these electrons are, when they get excited, when they come back down, kind of brought us to Bohr's theory or Bohr's model of the atom. This over here with the like different rings for energy levels is Bohr's model. Okay, so Bohr's model kind of says, oh, well, there's an energy level 1 and an energy level 2 and an energy level 3 and so on and so forth. And the electrons can kind of go from one to the other if you excite them enough. Okay, so his theory is that electrons absorb energy to, I'm going to put in quotes, jump. Okay, they go up to another energy level. So jump to a higher energy level. Okay, this is called an excited state. Excited state. Okay, so electrons absorb energy to jump to a higher energy level, and then when they go back down, they give off energy. Okay, so and release energy to fall, I'm going to put that in quotes too, so they either jump up or they fall down, back to what's called their ground state. So the low energy level that they sit in is their ground state. The high one that they jump to is called an excited state. Back to ground state. Okay, so Bohr noticed that electrons, at least in hydrogen, this is what they were doing. And he put an equation to it, and we could actually calculate where those electrons are based on the light that they give off, which was kind of cool. Now, like I said, this equation only works for hydrogen, not for anything else. So after that, we just had to test to figure out where all of those wavelengths are at. Okay, so what we're going to do in example 6 is actually use this equation, see if it matches up with one of the wavelengths that we're seeing. It says, and if you printed off the notes, the rest of this question is probably covered up. I apologize for that. It says, what wavelength of light is generated when a hydrogen electron falls from n equals 3, so the third energy level, down to n equals 2, or the second energy level. So all you would do is plug it into this equation up there. And no, you don't have to memorize that equation. I would give that to you. 1 over wavelength equals 1 times, oh no, sorry, I missed some numbers there. 1.097 times 10 to the 7th times 1 over, okay, so it says NF squared. So that's where it ends up, its final energy level. So if I'm going from 3 to 2, that means 2 goes here, squared minus 1 over ni. So that's where it started. It started at n equals 3. So that's 3 squared. And that's it. Okay, so again, watch your calculator on your order of operations. You should get that 1 over wavelength is like 15.2361. And then algebraically, you can do cross multiplication, or you're really just doing 1 divided by this number. And you should get that the wavelength is 6.6 times 10 to the negative 7th meters. So that means when an electron goes from the third energy level back down to the second energy level, it gives off a wave that has this wavelength. And that actually matches the Bohr model that I have up here, this 357 nanometers. That's 6.6 times 10 to the negative 7th meter. So it's that red wave, or that red light wave, that's given off when that electron transition occurs.
Where do we get meters from? Is Bohr's theory just in meters? Is that equation just in meters?
Yeah, so all the equations I'm giving you are in meters. So anytime you're using an equation, you should always go to meters instead of nanometers. Nanometers is just, unfortunately, what we usually measure in, because that's where the visible spectrum is. But yeah, I'll just always go to meters. All the equations are in meters. Good question. Any other questions? Okay, I'm gonna take a break for a minute so you guys can, like, go to the bathroom, print something off if you need to, ask me some questions if you need to. I'm gonna start lecture back at 1:07, so in 5 minutes. If you want to hang out and ask me questions, you can do that.